So the data I used in my analysis was collected in 2019 by the STAR experiment. We are currently just across the sound from Long Island, New York, which is home to the relativistic heavy ion collider at Brookhaven National Lab. One of two operating experiments on the ring is STAR, which is the solenoidal tracker at RIC. And this is what I used for my analysis. But before we launch into my analysis, we all need to understand what a typical collision looks like at RIC. And so in our accelerator, the relativistic heavy ion collider is a 2.4-mile circumference ring with 1,740 superconducting magnets that accelerate and focus beams of particles in concentric directions, and such that they collide at in periodic intervals every few hundred nanoseconds or so within the experiment. So, and we do not collide just one ion with one ion, or one proton with one proton. We have bunches of these ions that we feed into the accelerator. And there's often about 1 billion gold ions, which are the gold nuclei with the electron stripped. And we collide these billions of ions in these periodic intervals within the experiment. So when they collide, they hit each other at some primary vertex within the part of the detector. And we can characterize the amount of energy within these collisions by using the Lorentz invariant quantity S, and which is defined above. And so the center of mass energy used in the 2019 run of STAR was 200 GeV. So this is the energy of the collision of these gold ions. Now, when these Lorentz contracted pancakes collide at the heart of the detector, the hadronic matter is dissolved, and the constituent quarks and gluons within the confined hadronic matter are practically melted into this plasma that we call the Quark-Gluon plasma. And a whole slew of particles is emitted from the source of that collision, along with various interesting physics observables, such as jets, highly energetic streams of particles, which we will get to later in the presentation. Now, RIC is renowned for its discoveries regarding the Quark-Gluon plasma, which we remarkably found to be a very dense colored medium that exhibits liquid-like properties that follow hydrodynamic relativistic flow with minimal viscosity to entropy ratio. So once we surpass some critical temperature in the medium of about 155 MeV or mega electron volts, which is approximately 2 trillion degrees Celsius, or many thousands of times hotter than the interior of the sun, the confined hadronic matter dissolves and melts into this sort of quasi-free colored partons that interact strongly. And this plasma is only formed 1 femtometer by C after the collision and has a lifetime of about 10 femtometer per C. And through our models, we have found that it resembles that of a relativistic hydrodynamic fluid. Now, hard partons, or very energetic particles created by the initial collision, are established at the very instant of the collision, whereas the Quark-Gluon plasma takes about 1 femtometer per C to form. So these highly energetic partons, or hard probes, experience the entire evolution of the Quark-Gluon plasma and act as an excellent proxy for observing the energy loss of the plasma and the characteristics and behaviors of the plasma itself. Now, if we zoom into the interaction region of the collision, we see that because we are colliding things that are so small and trying to focus them at a single point, we will never collide them exactly head-on 100% of the time. So oftentimes when these nuclei or bunches collide, they collide with some impact parameter at a centrality that is not exactly head-on. And so we quantify this with something called centrality, and this is a measure of how head-on or how peripheral the collision is. And in this coordinate system, the beam axis is coming towards us, so you can envision these nuclei coming at each other as such. Now, when they collide with this initial position state anisotropy. And this difference in shape of the collision, this lumpiness, due to initial state fluctuations, induce different pressure gradients along different directions, which then are translated to an anisotropy in momentum space, allowing the QGP to expand asymmetrically. And so we can model the interaction region of the Quark-Gluon plasma as this non-circular ellipse, or a 3-dimensional rugby ball, if you will, where it has a minor axis and a major axis with that we define by using a construct called the reaction plane. Now, the reaction plane is defined to be the plane spanned by the beam axis vector and the impact parameter vector. So again, coming towards us and going up. So the minor axis of this elliptical Quark-Gluon plasma is deemed to be in plane, whereas otherwise it is out of plane. Now, what does this mean in terms of energy loss and measuring different observables? Well, the bottom line is that if there's more Quark-Gluon plasma, there are more potential color interaction sites for these partons to interact with the medium and lose energy, whether it be through collisional means or radiative means. So elastically transferring kinetic energy or emitting gluons through gluon Bremsstrahlung. So particles that travel out of plane or along this major axis of the ellipse will traverse through more Quark-Gluon plasma than those traveling in plane, and thus have more opportunity to interact with the colored medium and lose energy. So by studying the yields and energies of these particle sprays with relation to this anisotropy Quark-Gluon plasma can probe our path length dependence theory and enable us to observe whether or not this theory of traversing more Quark-Gluon plasma causes more energy loss. So the two primary subdetectors I used in STAR are the time projection chamber and the event plane detector, pictured here respectively. The time projection chamber is used to measure the form momentum of charged particles, whereas the event plane detector, one on each side of the main barrel of STAR, detects the azimuthal distribution of emitted particles in the forward and backward directions. And so by using different detectors to measure different quantities, I can reduce the autocorrelations in my study that could work the effects. And so I use the time projection chamber to measure the jet and track spectra of transverse momentum, and the west and east EPD, or event plane detectors, to calculate Q2, which is a flow parameter, which I will describe later, and the event plane itself. Now, we get to another word in my title, jets. What are jets? Jets are very highly energetic collimated sprays of particles that are a result of an initial hard parton created in the initial collision that then undergo energy loss through traversing the plasma and fragment, hadronize, and decay into this conical shape of reconstructed energy. The goal of jets is to describe the physics of those initial partons, but we can only do so at the detector level. So these act as an excellent observable. And you can see here an event display where two jets are created back to back by conservation of momentum. And we see on this plot that with increasing centrality, the range of jet PT broadens, meaning that you can obtain more highly energetic jets at more head-on collisions than you can at more peripheral collisions, because a harder momentum transfer can occur in a central collision. And we define transverse momentum to be the magnitude of the momentum in the transverse plane perpendicular to the beam axis, meaning away from the beam line where the input beams are coming from. I also use a technique called event shape engineering, which enables us to select on the centrality and shape of a collision, which are related but independent parameters. And this will enable us to select on eccentric events versus circular events by measuring the Q2 value, which we'll talk about in the next slide. But as you can see, for central collisions, we can obtain high momentum values, but low ellipticity, which is what Q2 measures. Whereas for peripheral collisions, we can expand into the elliptic shape of the collision while reducing the amount of energy within the jets. So what is this Q2 value that I've referenced a few times? Well, it is dubbed the second order reduced harmonic flow vector. And the harmonic flow vectors are a way to describe the overall initial state of the collision and as it expands. And so the second order harmonic describes the elliptic shape of this collision, which we're interested in for probing the path length dependence. And it's defined to be the magnitude of this vector normalized by the particle multiplicity of the event, or number of particles produced. And if you stare at this equation long enough, you can convince yourself that if there is a radially symmetric distribution of particles in this azimuthal angle phi, Q2 will evaluate to 0. But if there's some concentration in different pockets along the radial direction, then Q2 will grow higher to 5 or 6, which we will see in our plots. And so it's an excellent way of quantifying the ellipticity of an event. Now, if we examine the relationship between Q2 and collision centrality, we see that as we increase in centrality, the average Q2 value monotonically decreases, though we still obtain a wide range of Q2 values for each centrality class, hence the need to select on the highest and lowest 10% Q2 values per centrality class of collisions that we look at to ensure that we are indeed observing different events from central radial events to elliptical events. And in this plot, we can see that as the centrality becomes more central, Q2 is smaller, whereas with more peripheral collisions, the green plots, we obtain more elliptical events and a broader spread. So the last piece of the puzzle is describing the event plane. So the event plane is the plane characterized by the elliptic spread of the particles. And we define in plane to be a plus or minus 15 degrees away from this event plane on either sides of the plane, and out of plane to be that same distribution with a phase of 90 degrees. And so when we look at jet yield with respect to this event plane, we see that we on average reconstruct more in-plane jets, the orange points, rather than out-of-plane jets, the green points per event in this centrality range. So this is an initial indication of some path length dependent behavior that must be investigated further. And we can also examine the jet yield ratios, or the out-of-plane to in-plane ratio of jets that we find. And if there is indeed a path length dependence, we would expect this ratio to be less than 1, because we expect a suppression of out-of-plane jets with respect to in-plane jets. And this, so far, this is what we see. We see higher Q2 events being more suppressed in relation to this ratio than the low Q2 events, and they are indeed less than 1. Now, my colleague Ryan Hamilton is doing phenomenological and computational studies in analogous domains to my research. And in his simulations, he's calculating eccentricity, which is a parameter analogous to ellipticity. And he sees the same behavior, that central collisions display less ellipticity than the more peripheral collisions. So this is a good check. Likewise, using the Glauber model, which is a theoretical model that models centrality and participating nucleons in the collision, he also sees that with increasing centrality, we have this monotonic decrease in ellipticity, still with a broad range. So this is another check. And lastly, I can also examine the charged track spectral ratio. So before we cluster all these tracks into jets to try to reconstruct all the energy of that initial hard parton, we can look at the individual tracks. And this is the distribution that we see of large Q2 events to small. It's roughly 1 and displays an interesting shape that is comparable to previous results. So we are working towards establishing this plot for jets rather than tracks. So lastly, the current status of the project is that the track spectra you saw on the previous slide align with results established last year by Isaac Mooney, and the centrality and shape correlations align with models thanks to Ryan's studies. And we are seeing initial indications of a path length dependence because the measurements are in the right ballpark, though still not with high certainty because of being bounded by low statistics and still high uncertainty. So in the coming weeks and months, I'm going to ensure that the jet statistics are comparable to recent analyses that use the same STAR 2019 data, work to boost statistics to increase our, or rather decrease our measurement uncertainties, implement statistical uncertainties of our own, and then compare with further theoretical and simulation expectations. And so with that, I sincerely thank everyone on this slide.
Any question? So can you, very nice thought. Can you go back to the slide with the model and then your data? One of you. Yes. Yeah. So I guess they are like qualitatively similar, but did you have it? They still look different by eye. Do you have any theories as to why they might be slightly different?
I don't know the mathematical definition of eccentricity, but it does differ from that of the Q2 harmonic. So I think in that definition, it will have, and because this scale for eccentricity is from 0 to 1 and mine is from 0 to 5 or 6, it will get warped in some fashion. And just because of the way that it's defined, it's measuring slightly different things. And so they're not exactly the same parameters. So this is like looking at centrality versus flow. They're related but independent. And so although the things with centrality won't always give the same things as the things that, as the events with some flow, I think the same things occurring here where the observables are just different. So although they agree qualitatively,